Welcome. Today we're diving deep into a really fundamental question in computer science, P versus NP.
It sounds abstract, maybe,
hmm
but it's got huge implications.
Yeah, we've got a set of questions here to sort of guide us, help us unpack it. Our goal is really just to get to the heart of what this problem is and why it matters so much,
Right. And it starts with this idea of computational complexity.
which is basically a way to measure how difficult problems are for computers, especially as they get bigger.
Exactly. It helps us classify them, understand what's feasible to solve and what isn't, practically speaking. Why some things are instant and others take forever.
Okay, so let's start with the first classification. Class P. What does that mean?
P stands for polynomial time. A problem is in P if there's an algorithm that can solve it uh, relatively quickly.
Quickly meaning in polynomial time. Can you give us a feel for that?
Sure. Imagine the time it takes grows, maybe like by the size of the input squared or cubed. That's polynomial. It's manageable growth.
Okay, so not some crazy exponential explosion of time. These are the problems we consider efficiently solvable.
That's the idea, yeah.
All right, so what about the other side, class NP? How's that different?
NP stands for non-deterministic polynomial time, which is a bit of a mouthful.
Hey, yeah, what's the core idea?
The core idea is about checking an answer. For a problem in NP, if someone gives you a potential solution, you can verify if it's correct or not in polynomial time.
Ah, okay, so checking is fast, but finding the solution might not be.
Exactly. Think of a Sudoku puzzle. Filling it out can be really hard, right?
Definitely.
But if I give you a completed grid, you can check if it follows the rules pretty quickly. That's NP. Easy to verify.
Got it. Hard to solve? Maybe, but easy to check. So that leads directly to the big question, doesn't it?
The million-dollar question, literally. Is P equal to NP?
Meaning, is every problem whose solution is easy to check, NP, also easy to solve?
Precisely. That's the P versus NP problem. And nobody knows the answer for sure.
Why is finding out so important? You mentioned implications.
Oh, massive implications. Take cryptography, like online security.
You're right. You mentioned that, like
Yeah.
the systems protecting our data.
Yeah. A lot of modern encryption relies on certain problems being computationally hard to solve, even though checking a potential solution is easy. Factoring large numbers is a classic example.
So that's believed to be an NP, but not in P.
That's the common assumption, yes. If it turned out P does equal NP, it would mean there's an efficient way to solve those hard problems.
Which would mean breaking the encryption.
Potentially, yes.
Hmm.
It could render much of our current cryptographic infrastructure obsolete. It's a huge deal for security.
Wow, okay. That's significant. Are there other examples of these NP problems? Maybe ones that feel a bit more concrete?
Sure. A famous one is the traveling salesperson problem.
Ah, yeah, I've heard of that. Visiting cities, shortest route.
Exactly. Given a list of cities and the distances between them, find the absolute shortest possible route that visits each city once and returns to the start.
Okay. Checking if a given route length is below a certain target seems easy enough.
Right, polynomial time verification. But finding the actual shortest route, that becomes incredibly hard very quickly as you add more cities. It's what we call NP complete.
NP complete, meaning it's one of the hardest problems in NP.
Essentially, yes. If you found an efficient polynomial time solution for any NP complete problem, you'd automatically have one for all problems in NP, which would mean PNP.
Gotcha. And circling back, this polynomial time, that's really the benchmark for efficient.
It's the generally accepted theoretical boundary, yes. Algorithms that take longer, like exponential time, just become impractical for inputs that aren't tiny.
Okay. And briefly, what about NP hard problems? How do they relate?
NP hard problems are at least as hard as the hardest problems in NP. They might not even be in NP themselves, meaning checking a solution might not be easy either,
Right.
but they're definitely in that very difficult category.
So this isn't just some academic curiosity.
Absolutely not. The P versus NP question is one of the 7 Millennium Prize problems selected by the Clay Mathematics Institute.
Meaning there's $1 million prize for solving it.
Correct. Which highlights just how significant and difficult it's considered by the mathematical and computer science communities.
So wrapping up, the central tension is we know how to quickly check answers for a whole class of important problems, NP, but we just don't know if there's always a way to quickly find those answers, P.
That's the core of it. Are finding and checking fundamentally different in terms of difficulty or not?
And the answer could, well, change the world as we know it.
It really could. From medicine design to logistics to AI, an efficient solution to NP problems would be revolutionary.
Which leaves us, and you, with something to think about. How much of our daily digital life, our security, our systems, relies on the assumption that P does not equal NP? What happens if that assumption turns out to be wrong? Something to ponder. Thanks for this fascinating deep dive.
My pleasure. It's a deep topic.